It seemed like we got a couple of people who added, a couple of people who dropped, so we're going to move right on ahead and begin with chapter 1 from our book, Principles of Fire Behavior and Combustion. First chapter, chapter 1, dealing with fire measurement and the SI system of units. Let me pull up the screen. So here we are, chapter 1, fire measurements and the SI system of units. So we're going to explain the importance of measurement, name some of the basic units, and go from there. Understand the precision of a measurement, explain the difference between mass, weight, and energy, heat, and enthalpy. Some things about measurements. It's kind of one of the keys to understanding fire phenomena. You know, we talk about a lot of different variables, a lot of different things in fire. And so if we understand what these measurements mean, it's going to help us better understand what fire is. So some of the things that we can ask, you know, when did the fire start? There we're dealing with the measurement of time. How rapid did the fire grow? Again, dealing with some time. How hot? This can deal with, you know, not only temperature, but how much energy was burned or consumed, and how severe of a threat. You know, we're going to look at some of those things that deal with, you know, how much potential did it have? How much fire load was there? Different things like that. So in our books, we're starting there on chapter 1, page 2. If you guys follow along, this will follow right through with the book, which will help you as you're preparing for your quiz. So when we talk about the SI system, the SI units comes from the name Sistema Internacional de Unites. I don't know if I completely murdered that or not, but the SI unit is basically an international measurement system, also known as the metric system. Here in the U.S., we use the English system, you know, where we deal with feet, inches, miles, pounds, things like that. The SI system deals with things like meters, you know, decimeters, centimeters, kilometers, and dealing with kilograms, different things like that. So as we look at the different things, we're going to talk about mass, length, time, electrical current, temperature, and we're going to break these down into what they cover. The SI system is an adoption led to quantitative communication. So what this enabled things to happen was, you know, if I'm talking to you and I say, hey, this 1 meter long, or it's 2 meters long, it gives you an idea. You know what I'm talking about when I mention a meter. It gives us that same kind of communication. You know, it's much like speaking the same language. You know, if we're speaking English, we know what certain words mean and how they go together and how we use them, and we're able to communicate, whether it's Spanish, English, or whatever the case may be. Those words that go together, if we understand that common theme, that's going to help us in our
that's fine, whatever.
In our talking. The precision of limits is going to exist according to the measuring instrument. So if we're looking to measure something, you know, if you're doing construction, you use a measure tape or a tape measure, and it's going to break it down to the 16th of an inch. If we're looking at, you know, we're doing some machining on a lathe or something like that, we may use something called a micrometer, which is going to measure things at a much more precise level. You know, there are some times where it's okay to estimate the calculated value, you know, as we need. You know, hey, I may say, hey, give me something that's about 24 inches long, or give me something that's about 1 meter long, whatever that case may be. I'm looking for that not necessarily a precise measurement, but, you know, an estimate or something fairly close to it. And like I say, this is all going to depend on what we're doing.
Money. 1,700. So
sorry, 1 second.
That's mine, or what's going on? Because they're asking for me.
If I could have, if you guys are if you guys are following along, if I could have you guys mute your mics just to keep the background noise down, that'd be appreciated. So we talked about a meter. The meter is the basic SI unit of length, and it can be defined as the length of path traveled by light in that much of a second. So basically that's how the scientific definition of what a meter is. If you look on page 3, you'll see, and this is going to kind of help us here in the United States to kind of get an idea of how long those are, but we see that 1 meter is 3.28 feet, and we see that in the table there. Like I say, this is just to kind of give us an idea, you know, give us some point of reference and that type of thing. The kilometer is basically 6/10 of a mile, and so on. We see that a centimeter is about 4/10 of an inch, so just under half an inch. So that's going to give you just a little bit of an idea of what each of those units means. The SI dimensions are in multiples of 1,000. So we have a kilometer, which is 1,000 meters. We have a meter. We have a millimeter, which is 1/1000th of a meter. You know, we do see some others that it's broken down. Again, these are broken down in multiples of tens. We have a centimeter, which that breaks a meter into 100. A decimeter breaks a meter into 10. So there's just different ways of breaking things down versus, you know, 1 inch. And then 12 inches equals a foot, 5,280 feet equal a mile. So it's just a little more standardized in the SI system. There we see that chart there with a few of those things that we talked about. So as we deal with these units, dealing with meters and centimeters, kilometers, one of the things that we're going to use it in is in finding area. Now, where may determining the area of something be important? This may be in something, say, as we're trying to roughly determine the size of a building. You know, how big is that building? Is a 100 square foot building much different than a 10,000 square foot building? Absolutely. If each of those was fully involved with fire, that's a huge difference between those two buildings. A 100 square foot building may be a small shed. A 10,000 square foot building is going to be maybe a large commercial warehouse or something like that. So determining, you know, what that area is, and the way we do that is we take the length of the surface and multiply it times the width of our surface. So if we have a 10 foot by 10 foot building, we multiply those two, 10 times 10, that's going to give us 100 square feet. Or if it was a 10 meter by 100 meter building, that's going to give us 1,000 square meters. So that's how we determine the area. It's a two-dimensional measurement of the length times the width of a surface. So we see that the English system, the equivalent, and what we use, you know, we may measure in square inches to determine area or square feet. Some of the larger areas are measured in either hectares, or what we use in the United States is acres to determine larger sizes of area. This may come into play when we're dealing with grass fires or wildland type fires when we're determining acreage of these fires, because it's much bigger than just square footage. Sometimes we use some of these calculations for fire dynamics and determining, you know, how cross-sectional area of vent for flow through the vent, you know, how it's going to flow through that certain area. An area of a hot surface for heat transfer to colder objects could also be a time where we're looking to determine the area of an item. Now, as we move from area, we look at volume. Volume takes in a third dimension. So if we think of volume, we think of like something such as this cup of water to determine, you know, for a rectangle, we're going to take the length times the width times the height of it to determine the volume of that item. As we use this in the SI system, we're going to see that it could be in cubic centimeters. For the US, we may use gallons or quarts in determining that volume. Now, this volume may be a liquid, or it may be a liquid or a gas inside that container. As we continue on, we talk about mass and density. Mass, the basic SI unit of mass is a kilogram. So we see that 1 kilogram equals the mass of 1 liter of water. So we see that the kilogram weighs approximately 2.2 pounds. Now the thing with mass and weight, such as pounds, they're a little bit different. If we look at on page 4, it says the mass of an object is a fundamental property of the object representing the quantity of matter in the object. By comparison, weight refers to the force acting on an object because of gravity attraction and is a convenient way to measure mass on Earth at sea level. So we will see some differences in weight where it depends on what your elevation is, because it's the amount of that gravity attraction of that object, of the mass of that object. Whereas mass is kind of the total substance that makes up that whole item. When determining density, we may use things as grams per centimeter cubed, or kilograms per meter squared, or pounds per foot cubed. So as we use mass and density units, we use these to denote relative prevalence of components, such as a concentration. This is the component mass per unit volume. So the concentration of, say, a bleach concentration is going to tell you how much bleach is actually in that total jug. You know, a gallon of bleach isn't pure bleach unless it's commercial grade or something like that, but it's got a percentage. That's that concentration of actual bleach within that gallon. So time units, these are the same in the SI and the English system. The basic unit is a second. Then we have an hour, or excuse me, a minute and an hour, day, year, those types of things. So those measurements are the same in both of those systems, the SI and the English system. We continue on with these. We see that with the units of time, we can have things such as speed. This is a rate at which an object is moving. So speed may be like meters per second, kilometers per hour, or as we use in the US, miles per hour. Now velocity is speed in a chosen direction, whereas acceleration is the rate of change of speed. So let's say you may be driving 55 miles an hour. As you accelerate and you go increase up to 65 miles per hour, that's acceleration. That's that rate of change from 55 to 65. So it's a little bit different than the speed with which you're going. It's just that rate of change of that speed. As we deal with force, this deals with a lot of movement. Force needs to accelerate a mass of 1 kilogram at the rate of 1 meter per second squared. So this English system would be 1 pound of force will accelerate 1 pound of mass at the rate of 32.2 feet per second squared. So this is force. This is dealing with movement. Pressure, we think about like air pressure, water pressure, things that are being forced through an item, such as the pressure with which water is being forced through a hose. We use things as pounds per square inch, PSI. And the basic SI unit of pressure is a Pascal. PSI may come into play as you guys are beginning to become fire engineers, where you're pumping and things like that, where you're trying to determine how much pressure do I need to get the correct flow of water at the end of the hose. Dealing with enthalpy and energy units. So fire generates energy. This increases. We see that a fire in a closed constant volume system generates energy. This increase in energy transfers heat to the system, raising the pressure within the volume and increasing the temperature of the gases, the combustibles, and the box itself. Of course, most fires occur in an environment of nearly constant pressure. Even a small pressure increase breaks a window and otherwise speeds the combustion process out of the room of origin. So when this augmented energy is released, it's as the increase, this is defined as enthalpy, and this is on page 7. And it is the parameter that is properly considered in characterizing a fire. The use of the term energy release has been widely misused as synonymous. If enthalpy increase as a whole simply raises the temperature and expands any gases that are present, then the enthalpy change is equal to the heat released. So heat is being generated And this enthalpy is that heat above that's being released. So fire generates energy. This increase transfers heat to the system we talked about. So if we have a box, we're going to talk a lot about boxes. You know, a box may be a room, a box may be a vehicle. But as this heat transfer takes place to that system, within that box, let's say we have a room and contents fire, that pressure within that volume, within that room is going to increase. The temperature is also going to increase as that fire generates energy, and it's going to increase the spread outside the room. So as we look at these, we see that the unit of measurement for these is a calorie, and that calorie or a joule, which is more, we see there, the calorie equals the energy needed to heat 1 gram of water by 1 degree Celsius. Then we talk about the heat of combustion, effective heat of combustion, and this may be foot-pounds or BTUs. This is going to be, you know, what's given off. That heat of combustion is that amount of heat that's given off as something burns. Power, this is the rate at which enthalpy or energy is expended, so the rate at which it's used. The SI units are watts. The English units are horsepower or BTU, like we said. Temperature units, in the English system, we use Fahrenheit. In the SI system, we use Celsius or the Kelvin scale. So in the SI system, we see that in Celsius, that water freezes at 0 degrees, water boils at 100 degrees. In the English system, again, we talked about the Fahrenheit scale. Water freezes at 32 degrees. Water boils at 212 degrees. You see conversions down there. For many of these conversions between the SI system and the English system, there's formulas that we can use. We aren't going to get so much into that in this class. We're just more trying to understand why these units are being used, and that, you know, if you need to, you can convert between them. One of the things that you're going to find in this class is we're not going to worry a lot about the specific calculations. There's some other sections in here that deal a lot more with calculations and things like that. But we're trying to just give you guys a good understanding of the fire behavior, and that's going to help to make you a better firefighter. There's kind of 2 things that you really need to understand to become a better firefighter, and that's building construction, how buildings are built, which is going to help you understand how they're going to burn and things like that, and where it's the fire is going to go, as well as fire behavior. So as I see a fire ahead of me, if I know what's burning, if I know how it's going to burn, if I know where it's going to go, that's going to help me in extinguishing the fire or making those determinations of my next tactical decisions to be sure that I'm making the correct ones, and that the fire is not growing, but that the fire is getting smaller as I want it to do. So again, conversion factors, you know, we looked at some of the things like a meter, you know, we talked about that being 3.28 feet. We talked about, you know, a kilogram being 2.2 pounds, you know, things like that, or some of those things you may just want to kind of tuck away in the back of your head. I know for us, in the EMS world, you start looking at, you know, some of your medication dosages deal with kilograms. So you got to be able to think quickly, how do I convert, you know, someone's weight that I've estimated to a somewhat accurate kilogram, so I don't overdose the person with too much medication or not give enough to help take care of the problem that they're having. So as we look at the summary of chapter 1, we look at some of the things that we want to have the ability to measure, to quantify, some of the essential understanding and essential information of fire phenomena. Some of the basic measurements for fire phenomena are time, length, area, volume, mass, density, force, pressure, enthalpy and energy, power, and temperature. There are multiple units for each of these measurements, whether it's metric or English. The metric units are most widely used throughout the world. The English units remain in use in the US. Familiarity with various units and their interconversions can minimize the change of making a serious calculation error. So as we look at this, if you guys want to go back to page 2 in your book, if you guys don't have your books, you may want to jot down just a few notes. I'm going to share with you a few things that you may want to look at in preparation for your quiz next week. Some items that you want to go over and and look at. So on page 2, one of the things it talks about in the second column, it says the current international system, also known as the metric system, is the SI system. So that's something that you're going to want to know and understand. On page 3, under length, area, and volume units, it says the basic SI unit of length is a meter. As we move through on page 3 also, you're going to want to know and understand that a meter is approximately 3.28 feet. On page 4, in the left-hand column, area, it's in the third paragraph, top of that third paragraph, it says area is two-dimensional, and for a rectangular flat surface is the length of the surface times its width. If you go down to the beginning of the next paragraph, it says volume is three-dimensional. For a rectangular space, such as a room, it is length times the width times the height. Then go down to the next sentence, and it says the liter is commonly used as a unit of liquid and gas volume and is the same as 1 cubic decimeter. And then under mass and density units, the basic SI unit of mass is the kilogram. As we move through our books, some of those blue terms you may want to look through as you guys review just to make sure that you understand what those are. We're going to look at the top of page 6, and it says acceleration is the rate of change of speed. So I would know and understand what acceleration is. In the first column, partway down on page 7, it says power units. Power is the rate at which enthalpy or energy is expended. Then on page 7 also, temperature units, it says 2 temperature scales are used in the SI system, the Celsius scale and the Kelvin scale. So these are the things that you're going to want to know and understand in the first chapter. Again, we're going to go through these terms. And like I said, these first 4 or 5 chapters are kind of a review of some other scientific information that's going to be somewhat important to understanding fire behavior and combustion. If these don't make complete sense right now, just know and try and understand them the best you can, because we're going to be using these terms and they're going to begin to make more sense as we continue on through this semester. All right, we will move on to chapter 2 then, unless there's any questions on chapter 1. Does anyone have any questions on chapter 1?
Yes, I actually do have a question.
Yeah, go ahead.
I didn't exactly hear you for to pay attention for page 3 and 4.
Okay, on page 3, we looked at a meter. The basic unit of length is a meter.
That ass pallet ain't got none of them numbers. That's on the paper.
And then under a meter is 3.28 feet. That's in that text box.
Yes.
On page 4, we talked about area, volume, know and understand those definitions, as well as at the end of the paragraph under volume, it says the liter is commonly used as a unit of liquid and gas volume and is the same as 1 cubic decimeter. And then mass and density, the basic SI unit of mass is kilogram.
Awesome, thank you.
All right, no problem. Any other questions on chapter 1? All right, moving on to chapter 2. So chapter 2 deals with chemical elements and compounds, atoms, and molecules. So this is kind of like chemistry for those of you who enjoy chemistry. You'll probably be able to do very well in this class. One of the things that I want to encourage you folks, if you're moving into the fire service, you're going to need to take probably some biology type courses or anatomy and physiology, some other type of science courses that you may want to look into that could be very beneficial, include physics as well as chemistry. So if you haven't taken any of your science courses yet, those are maybe some of the things that you may want to look at as well. I know chemistry is very helpful in the hazmat world also, which is part of what we do as a firefighter. And then like anatomy and physiology, as well as even biology. Those things are something that are going to help you in the EMS world as well. So starting out, we are on page number 13 on chapter 2, page 13. Oops. Sorry, I started the wrong program. Right. There we go. Chapter 2, chemical elements and compounds, atoms, and molecules. So we're going to look at listing the chemical elements that are especially important in fire, describe atomic mass and dimensions, describe molecules, compounds, free radicals, and ions. Recognize the bonding features, further information about atomic and molecular properties. So if you look back more than 2,500 years ago, there was this theory that there's these invisible building blocks. For more than 25 years, they've had that there's something more that makes us up, something we can't see. Some of the early theories were based on faith and philosophy, some of the things that came out of those two realms. Then throughout the years, there's been experimental evidence and math that's shown that some of these are true. And now we have the technology to actually be able to see some of the structure and shapes of atoms. There's a joke that they say, why can't you trust atoms? And that's because they make up everything. Well, everything is made out of atoms. And so that's what we're going to break down is we're going to break things down to the most simplest things, dealing with atoms, elements, and that type of stuff. So an atom, all physical substances are made of chemicals. All chemicals are made of elements or combination of elements. And each element consists of one type of atom. So an atom is pretty much the most basic structure that everything else in the world is made out of. As we look at atoms and elements, each atom has a nucleus, which has a positive electric charge. And this nucleus makes up 99.9% of the atom's atomic mass. So its whole substance, almost all of it, is made up of this nucleus. Now, surrounding that nucleus, where that positive charge comes from, there's electrons that orbit around it. And these electrons have a negative charge. So you know that when we have a positive and a negative charge, they kind of keep each other in balance. If we had two positive charges, they'd want to push away from each other. Same thing with two negative charges. But that positive and negative charges want to kind of hold things together. And that's kind of what holds the atom together itself. The positive and negative charges balance each other out. So depending on what the positive charge of that nucleus is going to make a determination as to how many electrons are in that atom. Each element is assigned an atomic number. For example, the first element in the periodic table is hydrogen. It has an atomic number of 1, has a nucleus with an electron charge of positive 1, and it has 1 electron that's floating out here with a charge of negative 1, so it kind of balances itself out. Now this pattern continues throughout the list of all the elements. There are 118 known chemical elements. If you guys pull up the periodic table, you can be able to see those, or those of you who have taken chemistry previously, you have an understanding that there's 118 known elements. That's not to say there aren't more out there, because some of these have been discovered even in more recent years that have added to that number of 118. Here we see some of the most common ones: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. And so as we see these basic elements, these basic things, we know that, you know, the combination of them makes up different things. For instance, if we take 2 hydrogens and an oxygen, H2O, that makes water. Now, if we take something like sodium and potassium, or excuse me, sodium and, hang on a second, now I'm getting confused. No, sodium chloride. So sodium and chlorine, we know that that makes up salt, sodium chloride, you know, table salt. The mass is not dependent on the number of electrons. The electrons take up such a minimal part of the mass of the atom that it's not necessarily that significant of a portion of the mass. The discrepancy caused by neutrons, so inside that nucleus are protons and neutrons. Protons have a positive charge. A neutron has no charge at all. There are different neutrons within some of the same elements, which bind tightly with the protons to make up the nucleus. The neutron is a particle with a mass close to the mass of a nucleus, so a proton and a neutron have almost the same mass, but the neutron is electrically neutral. The heaviest naturally occurring element is uranium, which has an atomic number of 92. So you see that atomic number correlates to the number of protons in the nucleus, whereas you see the number of neutrons in uranium is 146. But we see that if you change the number of neutrons, that's, you see right there where it says U238 or 238U or 235U or 234U. We see that if we change the number of neutrons that are found in there, it does different things to that atom. So uranium-238 with 146 neutrons is very stable. If we take away 3 of those neutrons, which is not going to change the positive or negative charge of that atom, it's uranium-235, which is explosive component in atomic bombs, so very unstable. Most elements are made up of various isotopes, and that's what that was. Is the isotopes is when there's a different number of neutrons within the nucleus. Typically, 99% or more of elements' atoms belong to a single isotope. Some exceptions to the rule can include chlorine. You must know the atomic mass to calculate the combining portions of reactants. So as we look at some helpful measurements, hydrogen has 1 gram, carbon 12 grams, nitrogen 14 grams, oxygen 16 grams. Again, like I say, we're not going to worry so much about some of those calculations, but we're just kind of looking at the overall theories about these. One of the things in dealing with atoms, we talk about halogens. These halogens are important in fire retardant and fire suppression chemistry. So these include such things as fluorine, chlorine, bromine, and iodine. We look at the stability of atoms. For ordinary physical or chemical process, atoms may lose 1 or more electrons, share 1 or more electrons with another atom, or gain 1 or more electrons. And the reason they're losing, gaining, or sharing these electrons is to balance out. Again, we talked about hydrogen having just 1 electron. Hydrogen is also a diatomic atom, meaning that when it's found in nature, when it's in that happy state, there's actually 2 hydrogens to make the one for it to be happy. So we see that these changes can take place through extreme heat, striking the nucleus with the subatomic particle at or near the speed of light, or radioactive atoms with naturally unstable nuclei spontaneously emit charged particles from their nucleus. Molecules and compounds are still, atoms bind together to form a molecule. Their electrons can become shared. The forms one electron cloud and pulls the atoms together. The two nuclei repel each other, and the opposing forces create a stable nuclei. I'm sorry, I was incorrect with the hydrogen being diatomic, but some of the stable diatomic molecules include oxygen, nitrogen, and chlorine. But we look at if we have oxygen and it's stable and it's two oxygen atoms combined together, they're happy. If we add a third oxygen, it creates ozone, which is a completely different substance. Some single atom molecules formed at low pressures include helium and argon. Now, a chemical compound, so the previous chemical compound is molecules consisting of two or more atoms of different elements. So hydrogen and chlorine, hydrogen chloride, HCl, two hydrogen and one oxygen, water, H2O. But now look what happens if we add one more oxygen. We have H2O2, which is hydrogen peroxide, a very different substance than water, just by adding one more atom of oxygen. So as we talk about carbon, we talk about a solid element that reacts with oxygen to form stable compounds, whether it's carbon monoxide, carbon dioxide. But both of these can react with free radicals to form new substances. Excuse me. Chemical bonds and valence. Chemical bonds hold atoms together to form a molecule. The valence is the number of bonds an atom can form with other atoms. Atoms can have only a single valence state or multiple bonds. So hydrogen and chlorine, they have one bond. Oxygen has two bonds when it bonds together, has a valence of 2. Aluminum has 3 bonds, so it has a valence of 3. So these number of bonds or multiple bonds determines the valence of the atom. Carbon is a central element in most combustibles and unwanted fires because it can form all these different types of bonds. It bonds with a lot of different things in a lot of different ways. That's why carbon becomes kind of very important in fires. Carbon monoxide, something very common in fires. Carbon monoxide is the only molecule where carbon does not have a valence of 4. It only bonds with oxygen, and it's stable up to several thousand degrees Celsius. But it's a toxic gas that is found in all fires, this carbon monoxide. We look at 6 stable molecules with single bonds. We have hydrogen, hydrogen chloride, water, methane, methanol, ethane. Here's some different ways that these are portrayed. So we look at CH4, which if we go back one, that is methane. You see the C and then the 4 hydrogens surrounding it. This is one way it may be represented. CH4 may be represented in the plane with the C, the 4 H's around it, maybe a ball and stick, or a, let's see, this is the 3D model right here. And then again, this is showing number 3 shows the chlorine with the carbon with the hydrogens, the 4 hydrogens, and how they're bonded. That's what the different dashes and all that shows how each one is bonded differently. Here's a glucose molecule shown the same way, and you can see that they're just different ways to represent, the 6 carbons, the 12 hydrogens, and the 6 oxygens that make up glucose. So we look at some of those, the CH4 or the C6H12O6, that's the chemical formula. The planar structure is seen there in B. The perspective structure is D or C. The ball and stick model is D, and then the balloon model is E. So just all different ways to represent those chemical formulas. As we look at carbon dioxide, some other things, we see how they're bonds. You see the oxygen and carbon, there's double bonds between both of those. You see the acetylene, it's H with a single bond between the hydrogen and carbon, but the carbons are triple bonded. So those lines represent the types of bonds that are found in those molecules and compounds. Some different names. This is something that you're going to find in the hazmat world, that the way things are named can tell you a lot about the different substances, about the different compounds or molecules that you're dealing with. alkanes, alkenes, they all sound very similar, but we see that alkanes have a carbon-carbon single bond. Alkenes have one or more carbon-carbon double bonds. And what this is going to tell you is how things are going to react. So if we have something, and it may have just a single bond, we know that it may separate very easily. Or if we have something that has multiple bonds, it may not break apart as easy. So how those things do that, how they bond, helps us to understand the chemical makeup of something, but also how it's going to react. Moving through those, like I say, those are not necessarily as important to you right now, but it just goes give you some information on that starting out. Isomers, these are different arrangements of the same atoms. So here we see N-octane versus isooctane, dimethyl ether versus ethanol. It's the same makeup, but they're arranged two different ways to create two different types of substances. So that's an isomer. Ions, and when an electron detaches from an ion, it's known as a cation because it's got a positive charge. When a free electron attaches to a negative anion, or when it attaches to an atom, when a free electron does, that's a negative charge. It's an anion. An example of a solid crystal ions, which deals with ions, is sodium chloride. This is a balloon structure of a sodium chloride molecule. Free radicals are highly reactive in flames. These are things that kind of come off during the fire and combustion process, and it converts fuels into combustion products as well as heat and light. Free atoms are unstable, unattached atoms. Can include hydrogen, oxygen, nitrogen, fluorine, and chlorine. Normally form stable diatomic molecules. So as we look at physical substances are made from chemicals. Chemicals are made from elements or combinations, and elements consist of atoms. Building blocks of atoms are in the nucleus, which is the neutrons and protons, and electrons, and the shared electrons of atoms form bonds. Chemical bonds are broken and formed in fire, but atomic nuclei are not changed. Most combustible materials in fires are composed of organic chemicals. Standard ways to name organic compounds exist, but some compounds have acquired additional names as well. And we talked about that those names can mean things to what that chemical actually is. Isomers are compounds with the same elemental formula, but with different chemical structures and properties. And then free radicals and free atoms are unstable species central to ignition and continued flaming in fire. So that's that visible light, that heat, that combustion process that we're going to see. So if we go back to the beginning of chapter 2, which is on page 13, some of the things that we're going to need to know and understand is that elements, there's 118 known elements. That's right under the word element. The nucleus has a positive electric charge. Electrons, which are negatively charged. Again, those are some bolded words you're going to want to know and understand. And you're going to want to know and understand a neutron. That's out the bottom page on the right-hand column. It's electrically neutral, and it has the proton, the proton has a positive unit charge, but the neutron has an electrically neutral charge. Moving on to page 14 in that chart, we see that the first element atomic number is 1 for hydrogen, and it has a gram atomic mass of 1.00 grams, so it's nearly 1. On page 15, you're going to want to know and understand what halogens are. Moving on to page 16, the right-hand column, know and understand the word molecule. Atoms often bind to one another to form a molecule. So atoms of the same type are a molecule. Down towards the bottom of the page, we have molecules that consist of 2 or more atoms of different elements are known as a chemical compound. So something like oxygen would be a molecule, whereas something like sodium chloride or table salt would be a chemical compound. On page 17, in the first column down towards the bottom, it says the hydrocarbons containing 5 or more carbon atoms are liquid. As we move on, that is the items that you may want to know and understand for your quiz coming up. As we look at chapter 2, are there any questions on any of